Alright class, here's the last series of lecture videos. We've only got a few days left. We are going to have a test next week on acids and bases. It'll have a little bit of all three of these little subunits, titration being the last. So the whole point of titrations is that it allows us to find an unknown concentration of a different solution. If we know the reaction and we write out the equation, that gives us a ratio. Now a lot of the times we're going to have one-to-one ratios. Notice I have my acid in red, my base in blue, and I've written the products here in gray because they're neutral. Now the coefficients are a 1 here and a 1 here, so we have a one-to-one ratio. That tells us the moles of acid equal moles of base. Now this is only true when we have a one-to-one ratio. Here we can write that in an equation form. Now, from one of our earlier triangles, we know that moles is concentration, which is measured in molarity, times volume. And because the moles of acid and base are equal to each other, we can write the equation in this form. Concentration of acid times volume of acid equals concentration of base times volume of base. Quite often we're interested in finding the concentration of one of the solutions, in this case a base. Divide by the volume of the base. This is going to be given to you, and in a titration the two volumes are going to be measured. They're going to be measured in burettes, and you've seen some other videos on how to measure those. How does a titration actually work? Well, as soon as my slide will go to the next slide, we need to remember what's our definition of acids and bases. We're going to use the Bronsted-Lowry definition, saying that acids are proton donors and bases are proton acceptors. We also need to know some terminology like a strong acid or base dissociates 100%. Remember, dissociation means it splits apart. And something that is a weak acid or base will dissociate much, much less than 100%. Typically, we're looking at the highest around 5%, quite often 1% or less. Some other terminology in titrations is the equivalence point. That's where we have equal moles of base and acid, and an endpoint. Now, we can't see the actual moles of acid and base in our reaction, and so we need some outside thing to indicate when we're done. Well, that's where an indicator comes in. An indicator, which we looked at earlier, will change color, and if we've chosen the correct indicator, that will tell us the endpoint, because the endpoint, this color change, will happen very closely to when the moles of acid and base are equal to each other. One of the jobs of a chemist is to pick an indicator that has its endpoint near the equivalence point. So we're often going to use phenolphthalein. Phenolphthalein changes to this pink-like color at a pH of 8.3. Now, an acid and a base, if they're both strong acids and bases, will have an equivalence point at pH of 7. Now, it turns out that as you measure the pH of something, we start with our acid, we add more acid and more acid to our base. Suddenly, our pH starts to turn quite dramatically. Notice that on this curve, a pH of 7, the equivalence point, and a pH of 8.3 are separated by a tiny volume of extra base. Okay, so we have this titration curve. If you go to the Chem Guide reading link, you'll see a variety of different titration curves. You want to pick an indicator that changes in a pH range close to that equivalence point. This change in volume here, this between a pH of 7 and a pH of 8 or 8.3, is like a drop or two. In the notes, there are lots of links that you can go to, and I've put all of these in the titration resources. If we're going to solve for the concentration of the acid, we just change our equation. Instead of CaVa equals CbVb, divide by Va. That'll tell us the concentration of the acid. Okay? Depending upon what you're trying to find, you're going to rearrange this equation for the variable you want. Now, in some of these word problems, you might be asked, how much of volume do you need to neutralize a certain acid? Okay, so you're going to use this equation, but remember, you can only use this equation if you have a 1-to-1 ratio. You're only going to know if you have a 1-to-1 ratio if you write out a balanced chemical formula and you have 1 and 1 as coefficients. This is going to be a typical data sheet. Volume of acid used, you would measure this either with a pipette or a burette. You're probably going to be given the concentration of the hydrochloric acid, and that allows you to calculate the moles of acid you have in your reaction. Now we saw the balanced reaction with this for sodium hydroxide up above, so let's take a look at how we'd calculate moles of NaOH that will complete the reaction. Well, remember, concentration times volume gives us moles. Okay, so we can put this up here. This is a value that needs to be given to you. How can you find this? Well, moles is concentration times volume. Here's our concentration. Here's our volume. I've changed this to liters because it was in milliliters. I've divided by 1,000. Also remember that molarity is moles per liter. Per liter means it's in the bottom, and the liters cancel, leaving you with moles. Now, on a calculator, you're going to use your exponential expression or your EXP button, but typing, you might see this E. That means times 10 to the fourth in this case, -4. So let's take a look at that. We have our calculated moles of hydrochloric acid. There's 1 mole of HCl for every 1 mole of NaOH, and that's going to give us the same value in moles of NaOH. We cancel it. Here's another data table that you aren't going to look at because we're not doing titrations this year, but if you ever have to do them again, this is going to be the kind of situation you're looking at. Typically, you do a rough trial first, and you kind of figure out, all right, here's the volume total that I need, and then you are much more careful on the other trials. The advantage of using a rough trial is that you can add a lot quickly and then not worry about overshooting the endpoint, is how it's termed, but you know you're in this ballpark. And then you can add a certain amount. In titrations, it's called an aliquot, a measured amount, and then when you know you're close, then start adding a lot slower. That allows you to calculate the concentration of each trial, find an average, you can find a percent error, percent deviation, and work out the actual results from that. In the next video, I'm going to go through a number of calculation problems. So hopefully this helped you out.